Alright, so here I'm going to start out introducing the motivating question that we'll keep asking and answering. Are there any simple groups of order n? So usually the idea is to try to show there's a normal CeLO P subgroup. That one of the CeLO subgroups has to be normal no matter what. Note this also answers the question for something the textbook never talks about, characteristically simple, which means the only subgroups that are characteristic in G are the trivial subgroup and the whole group. In the same case, if a CeLO subgroup ends up being normal, then it's the only group of its order and therefore it's characteristic. So the same argument would actually prove a stronger result. And so in this video, we'll discuss the first method, for trying to do this type of argument. Overall, there's about 5 methods. And by methods, I mean outside of the first method, which is to just use the CeLO theorems directly and immediately get that one of the numbers has to be 1. This is cases where there's, the 0th method would be if you end up seeing that NP has only 1 as an option. But we're interested in the cases where for every prime, NP has more than 1 option. And this happens relatively frequently. The textbook points out that for n less than 10,000, an odd, and of course not a prime power, there end up being 60 cases where this 0th method does not work. It's actually possible for all the NPs to be more than 1. And yet not all 60 of those cases correspond to simple groups. So other methods are needed to actually prove that there are no simple groups in those orders. In fact, actually, we know there should be none because the odd order theorem says that every group of odd order has to be solvable. It mentions for n less than, I think, 500 that you quickly get, and even, you get a lot more bad examples. So, what is the first method? The first method is element counting. It's the method we've already discussed. But here it is again. To illustrate this method, we're going to let n be 351. So we're going to prove that there is no simple group of order 351. So first we note that this factors is 3 cubed times 13. And so the choices for n3, the number of CeLO 3 subgroups, it has to be congruent to 1 mod 3, and it has to divide what's left over when you get rid of the powers of 3. So it has to divide 13. And 13 is congruent to 1 mod 3, so 1 and 13 are the only options. Similarly, n sub 13 has to be congruent to 1 mod 13, has to divide 27. 1 and 27 are options. So this is one of those 60 cases because we can't rule out 13 and 27. But how many elements are there of order 13? So we'll assume n13 is 7, is 27. That means you have 27 CeLO 13 subgroups. Each one of them has 12 elements of order 13. And so that's 338 elements of order 13. What is left? Well, 351 minus 338 is 27 elements. However, we remember there has to be a CeLO 3 subgroup of order 27. And the elements in this group are all order some power of 3. So in particular, no element in this group is order 13. So these elements must be among these remaining 27, and in fact they must be all of them. So this tells us that the remaining elements form the CeLO 3 subgroup. Which tells us that this must be the unique CeLO 3 subgroup, because, well, if there was another one, there would have to be 13 more of them, and where are the other elements from the other ones going to come from? They'd have to come from the elements of order 13, but that's not possible. So we actually see that we get a normal subgroup. And otherwise, n sub 13 is 1, and there's a normal subgroup in that case. So this version of the counting argument is different than what I did before. Previously, the idea is you count the total number of elements of each order you can get. And if it adds up to being larger than the group, then there's a contradiction. And I noticed usually with counting arguments, you work best when your order factors as a product of distinct primes. That didn't happen in this case. When you end up having a power of a prime, what you hope to have happen instead is what happened here, which is that you focus on the distinct primes that have power 1, you count those elements, and you see whether or not you can force what's left over to form the CeLO subgroup for this prime with a higher power. So this method is most useful when you have distinct primes or when you have distinct, okay, let me say it carefully. When your order factors is distinct primes all with exponent 1, or distinct primes with exponent 1 except at most 1 prime. As another example, take n equals 105. So this one actually is in the textbook. That should factor as 3 times 5 times 7. What are the possible values for n3? Well, n3 could be 1 or 7. n5 could be 1 or 21. And n7 could be 1 or 15. So in this case we have distinct prime powers. Our hope is to count the number of elements of order 3, order 5, and order 7. in the case where you have 7 CELA 3 subgroups, 21 CELA 5 subgroups, and 15 CELA 7 subgroups, and see if this gives us a contradiction. So we're going to assume that these are the values, number of CELA subgroups of the corresponding primes. And so from here we're going to get 7 CELA 3 subgroups. Every CELA 3 subgroup has 2 elements of order 6. Order 3. Next up, 21 CELA subgroups. Each CELA 5 subgroups, each one has 4 elements of order 5. That gives us 84 elements of order 5. Finally, the last one is 15 CELA 7 subgroups. Each CELA 7 subgroup gives you 6 elements of order 7. That gives you 90 elements of order 7. Add them all up, read them and weep. 188, which is definitely bigger than 105. In fact, it's worth pointing out, if you look at these two conditions together, they add up to 98. And so that forces the remaining 7 elements to be in that CELA subgroup. So that actually gives us more information when N3 is 7 and N5 is 21. That actually forces N7 to be 1. In our case, this isn't as relevant, but it's worth pointing out when you get larger numbers of primes, it's possible for multiple primes to have a normal CELA subgroup. Also, from this approach, we see that if N7 were 15, then we have these 90 elements. There's 15 elements left over. And you might remember there has to be a CELA 3 subgroup and a CELA 5 subgroup. And together they can generate a cyclic subgroup of order 15. So in this case, the remaining 15 elements generate a cyclic group. That's still normal in G. So you can get some pretty powerful theorems just from counting elements. Although admittedly this fact needs a little bit more proof, because just because you have a group of order 3 and a subgroup of order 5 does not automatically tell you have a subgroup of order 15.